Continuing our discussion in section 4.3, we're discussing quadratic functions and their properties. In the first half, part A, all of our quadratic functions had exact vertex or vertices and possibly x-intercepts. Everything factored nicely and we ended up with nice whole numbers. However, sometimes quadratics are not factorable, and we got to be able to determine where their x-intercepts may lie. So we're going to be looking at the quadratic formula and the discriminant of those. Recall back from earlier sections that the discriminant will always tell us how many solutions a quadratic will have. The number of solutions it will have directly is proportional to the number of x-intercepts a graph will have. The number of solutions and the number of x-intercepts are in tune being the same concept. So let's look at the x-intercepts in general. If you have a discriminant where the discriminant is a positive number, meaning greater than 0, that means you have two real solutions, which in turn indicates you have two real x-intercepts. So the graph is either going to open up or it's going to open down. But you can see that you do have two x-intercepts either way. So the vertex is always going to be located from the prior video at negative b over 2a. That's how we find the x-intercept. And then we plug that into the function to find the y-intercept. Now, if the discriminant is equal to 0, if you recall back to when we discussed discriminants back in section 1.2, the discriminant, if it's equal to 0, you have one repeated solution, which indicates that you'll have one real x-intercept. So the graph of this, if it opens up, will come down, touch the x-axis and go back up, or same with the negative, it will touch the x-axis and go back down. So that's how you have one repeated real solution. So the vertex, the x will be located again at negative b over 2a, but the y is 0. Now, if the discriminant is less than 0, we have no real solutions and no real x-intercepts. So a parabola that doesn't have any real x-intercepts will be up here or down here. It never crosses the x-axis. But the vertex will still be the same, negative b over 2a, and the function evaluated at that particular x. So we're going to use this information to dig a little bit deeper. We already know how to find the vertex, whether it opens up or down, but now we're going to find the x-intercepts of the graph as well. So we're just going to keep adding on to the things we know about quadratic functions. So here I've got a quadratic in standard form, and we're going to find first the vertex. Recall, the vertex, we first find the x-coordinate. The x-coordinate is going to be located at negative b over 2a. In this case, is going to be negative 6 over 2 times 1. So that's positive 6 over 2, which is 3. So my vertex will be located at 3, comma, something. We have to find the y. To find the y, we take the function and evaluate it when x is 3. So we plug 3 back into this function, and we get 3 squared minus 6 times 3 plus 9. So that's 9 minus 18 plus 9, and that's 0. So we found the vertex. It's located at 3, 0. So I'm going to graph as I go. So if something looks a bit wonky or outside of what the parabola shape should look like, I know I've done something wrong. Now, does the graph open up or down? Well, based on the sign in front of the squared term, this is going to open up since it is a positive squared term. the x-intercepts. So to find the x-intercepts, well, this one's quite easy. I don't really have to do much work since we know that the vertex is located on the x-axis and it's going to open up from there. It's quite obvious that this has one x-intercept and it is actually located at 3, 0. But if I wanted to use the above chart to determine that, another way to do that is to plug it in and find the discriminant. So I'm going to do that here. Okay, so let's go ahead and find the discriminant of this particular function. The discriminant is b squared minus 4ac. So we have b squared, so that's negative 6 squared, minus 4 times a times c. So this is 36 minus 36, which is 0. And according to the chart, when the discriminant is 0, the number of solutions is 1, meaning you have one x-intercept. And we know that this graph is going to look like that because the vertex was on the x-axis. So when the vertex is on the x-axis, you know you have one x-intercept. Now the y-intercepts, I'm going to probably have 1. Since this is going to open up, it's going to cross the y-axis at some point right over here on the positive side. So to find the y-intercept, we always plug x in for 0. So we're going to substitute x is 0 to find the y-intercept. So up here, we're going to plug in x is 0. So f of 0 is equal to 0 squared minus 6 times 0 plus 9. So the y-intercept is located at 9. So I'm going to graph that point, which is up here. The axis of symmetry will be a vertical line which runs vertically through my vertex. So my axis of symmetry is at x equals 3. It is an equation, and that is the equation of the line. My domain, when I graph this together, since I know this is symmetric, I know I have another point over here. You can see that my domain is all real numbers. It goes from negative infinity all the way to positive infinity. However, my range does not start until I get to 0 and starts at 0 and continues to positive infinity. My graph is increasing just on this leg of the parabola. So it is increasing from 3 to infinity. It is decreasing on this leg of the parabola, so it is decreasing from negative infinity up to 3. Let's take a look at another one. Alright, so here's a parabola, and again in standard form. It does have a constant. This is a x squared plus bx plus c, where c is 0. So I sometimes like to fill in those missing terms just so I make sure I can recognize there is an a b, and a c, and I don't mistakenly use this as the c. So the vertex is going to be located. First find the x, which is negative b over 2a. So that's negative 4 over 2 times 1. 4 divided by 2 is 2. So I found the x-coordinate of my vertex. To find the y-coordinate, we take the 2 and plug it into the function. So 2 squared minus 4 times 2, that's 4 minus 8, which is negative 4. So I found the x and the y of my vertex. So if I go ahead and I plug those into my graph, I have 2, negative 4, which is my vertex. The sign in front of the square term is positive. So that means this graph will open up. So that means it's going to have 2 real x-intercepts. However, let's go ahead and find those to prove that it has 2 x-intercepts by finding the discriminant. Remember, the discriminant is b squared minus 4ac. So b is negative 4 minus 4 times a times c. This is where it's good to put the 0 in for c, so it's obvious there is a c and it is 0. So we have 16 minus 4, which is 12, and since that is a positive number, that means we will have two real solutions. So that was obvious also by the graph because we know it opens up, and it's obvious it will have two x-intercepts. So let's go ahead and find those x-intercepts now. So the x-intercepts we find by plugging y equals 0 into the original function. So when we plug y is 0 in here, we get 0 equals x squared minus 4x. And then in order to solve this, I suggest factoring, although you could use the quadratic formula if you prefer. So I have two x-intercepts, one at 0 and another at 4. So 0, 0, and another at 4. And that looks good to me because I know that the axis of symmetry is going to come down through my vertex, and my x-intercepts are equidistant from the axis of symmetry, meaning they are symmetric on both sides. So that makes me very happy. The y-intercept we find by plugging x equals 0. When we plug x equals 0 into the original function, if x is 0, you find that y equals 0 squared minus 0 times 4, so obviously y equals 0. So the origin was the x-intercept, but also the y-intercept. My axis of symmetry is a line that goes through the x-axis at 2. The domain is going to be all real numbers because it is a parabola. It extends to the left and to the right indefinitely. The range, though, however, does not start until I get to a y value of negative 4, but then continues indefinitely upwards. Again, it is increasing on the right-hand side. This is the increasing leg of the parabola. So it is increasing from 2 to infinity. It is decreasing on the left leg of the parabola. So it is decreasing from negative infinity to 2. So these are all of the details about the parabola you should know. So on to the last page. We'll keep discussing parabolas. Let's do one more example of what we've already been talking about. Here I've got a quadratic. It is in standard form. Let's go ahead and find the vertex. The x-coordinate is located at negative b over 2a. So this is positive, so this is positive 2 over negative 2, which is negative 1. So the x-coordinate is located at negative 1. To find the y-coordinate, we plug this negative 1 into the function. So it's going to be negative 1 squared minus 2 times negative 1 minus 3. So this is negative 1 plus 2 minus 3. So 1 minus 3 is negative 2. Now the sign in front of the square term is negative, so that indicates the parabola will open down. So if I have a vertex at negative 1, negative 2, and we know that this is going to open down, you can already guess how many x-intercepts this is going to have. None. But I'm going to prove it by using the discriminant form that we talked about earlier. So I'm going to go ahead and find the discriminant, b squared minus 4ac. So I'm going to do b, which is negative 2 squared minus 4 times a times c. We have 4. There's 3 negatives, so that means the negative 12, which is negative 8. And since this is a negative number, that means I have no real solutions, which means no real x-intercepts. And that was indicative of the graph that opens down. Is obvious it will never touch the x-axis. So we will have none of the x-intercepts. The y-intercept, we plug x equals 0 into the original function. So f of 0 is going to be negative 0 squared minus 2 times 0 minus 3. So we have a y-intercept at negative 3. The axis of symmetry is a vertical line that goes through my vertex. So my axis of symmetry is located at x equals negative 1. Remember, it will always match. The number from your vertex will always match the number in your axis of symmetry. And since I know this, every point on the right side is also a point on the left, I automatically have another point on the left-hand side. So a sketch of this graph will look like this, where the domain is all real numbers, and the range starts at negative infinity and stops at negative 2. The graph is increasing on the left-hand side, so it is increasing from negative infinity all the way up to negative 1. But then it is decreasing on the right-hand side from negative 1 to positive infinity. The last part to this section is finding a quadratic function if you're given key components like a vertex or another point. For example, let's find the quadratic function who's got a vertex at 3, negative 4, but it has a y-intercept at 0, 5. So sometimes I find it helpful to give a little graph of to what this might look like so far. So it's got a vertex at 3, negative 4, and this is my vertex, and it's got a y-intercept at 0, 5. So I know that my axis of symmetry looks like this. I know that since it's symmetric, it will have another point over here. So I already have a graph of what this is going to look like. I just need to find the equation of this line. So things I already know about it is it opens up, meaning that the first term is going to be positive. I know what the y-intercept is going to be, and I know what my vertex is. So let's use this information to see if we can find the other information it's asking for. So since the vertex is located at 3, negative 4, we know h is 3 and k is negative 4. And we know that the standard form of all parabolas looks like this from the first page. So we can plug in h and k to get a better example of what this graph will look like. So x minus h plus k, but in this case it's negative because we're shifting it down. Now the only thing we have left to do is we have to find a. That's where this point comes into play. This point tells us how far this has been stretched. Has this graph been stretched in any way? Well, to find the a, we're going to plug this information in. So when x is 0, y equals 5. We plug that in for x and y, and then we could solve for the missing variable a. So f of x is the same thing as y, so we'll say 5 equals a, which we don't know, we'll try to find, x is 0 minus 3 squared minus 4. So you see we only have one variable, which now we can solve for. So 5 equals a, this is negative 3 squared, which is 9. Let's add the 4 to both sides. And when you divide both sides by 9, you get a equals 1. So now I know a, which now I will plug back up into the original general function that we have up here. And when we plug all of that back in, we find that the function f of x is going to be equal to 1 x minus 3 squared minus 4. Okay? So this is the factored way to write a quadratic function. Obviously, we could write that in standard form if we chose to. All we would do is take this out of this factored form. So f of x would equal x minus 3 times x minus 3 minus 4, which is equal to x squared minus 6x plus 9 minus 4, which is plus 5. So this would be the standard or general form, and this would be the factored form of the exact same graph that we found down here. So either of those two graphs in the boxes are sufficient and give you this graph here. So let's try one more, just to practice one last time. To find the quadratic function whose vertex is at negative 1, 5, and whose intercept is at 0, negative 1. Following the steps we did up above, the first thing we did is we set the vertex equal to that, which means h is negative 1 and k is 5. And then we plug those into the general form of all parabolas, which is a x minus h squared plus k, and we plug those values in. Also, we'll plug in the values of x and y. X is 0 and y is negative 1. So f of x is the same thing as y. X is 0, h is negative 1, k is 5. So you can see I have everything in this equation except for a. So let's solve for a. So negative 1 equals, this is 1 squared, subtract 5 from both sides, and we have a equals negative 6. So if I take these three pieces of information and plug them all into the original general form of a parabola, we're going to have our equation. A is negative 6, where h is negative 1, so that means it actually becomes plus 1, and k is 5.